So this one's another biggie. It's called the ratio test. And if we were actually doing this whole chapter on series and the power series and Taylor polynomials and Taylor series, this would be great for finding what's called the ratio of convergence. That won't be on the AP exam this year, and we won't have time to cover it. Just know that if you end up taking this class in college, or if you need to review it, you might need to find out what that could be. So here's the ratio test. I just want to point out this is a series with non-zero terms. So none of the terms are going to be zero. No big deal. Most series don't have zero as one of the terms. And there's only one test. You take the limit. You pick out any term, and you have the next term there, the successive term, and then you check the limit as n approaches infinity. If that limit is less than 1, it converges. And as a matter of fact, it converges absolutely. We're talking about absolute convergence with the alternating. That can be true of other series also. It converges whether it alternates or not. It diverges if it's greater than 1, and if it equals 1, we're just really confused. You're kind of up a special creek without any paddles. Whoops. So it's that one test we have to look at. By the way, this is going to be really good for fast-growing functions. So if you're looking at something that is exponential or something with a factorial, this is the one that you want to use, the ratio test. It works well for everything, but especially for those fast-growing functions, that can be a hint for you. So here's a few examples. And remember, it all comes down to this limit right here. If it's less than 1, it converges. Greater than 1, it diverges. If it equals 1, that's probably not going to happen. Don't worry about it. So all this means is I have to figure out what would happen if I took the limit of the next higher term. So in other words, what would be the next higher term? Everywhere there's an n, I'm going to plug in an n plus 1. And I'm going to divide that by n factorial over 3 to the n. So the first thing I want you to notice is that, hey, whenever you're dividing these fractions, take a moment and realize that dividing by one fraction is the same as multiplying by another. Excuse me, multiplying by the reciprocal. What am I talking about? Okay, and now here's some crucial tips on simplifying this. You need to know something about these factorials. N plus 1 factorial, another way of writing that, is just n plus 1 times n minus 1 times n minus 2. Basically, this is the same as n factorial times the very next number. Also, this exponential here, 3 to the n plus 1, is the same as 3 to the n times 3 to the 1. So when I'm looking at simplifying this little limit right here, when you're doing the ratio test, almost everything, well, many things, will divide out. 3 to the n divided by 3 to the n. N factorial divided by n factorial. And what do we have here? I'm trying to take the limit of n plus 1 over 3. What's that going to get to? That looks pretty large. Maybe infinitely large. I don't think that's going to converge. Yeah, it turns out it really doesn't. That's going to approach infinity, and that's much bigger than 1, I think. I'll add it up in a minute. Okay, so you want to take these limits. By the way, I kind of cheat. I usually take the very next term. I plug in n plus 1, and then instead of dividing by this, I go right into multiplying by its reciprocal. Watch what happens on this next example. So a couple notes. I probably forgot the absolute values up here. Didn't really matter in this problem. Down here, you see that alternating part with the negative 1? This is an absolute value limit, so don't worry about whether it's positive or negative. But I took the very next term, ignoring that, n plus 2 becomes n plus 3, n plus 1. You get the picture, and I multiplied by the reciprocal. And only a little bit divided out, but oh, I get here and bummer. I'm looking at this limit going, oh, let's concentrate on the highest degree terms, and it